I'll give you a story, okay? He's now interested in cooking. If you refer to a authentic recipe which is present in a city's old library, in this very big library, he'll start searching the book. So he has shortlisted 3 books. Now there are some technical terms so that it can be done computationally, because obviously I cannot tell my computer to consider this story and give me. So we'll have to have some technical details, right? So let me add a technical layer on top of this. So let's do one thing. Let's see how does this transformer architecture would look like, and we'll take it from there. So when you search for, let's say, the transformer architecture, I'll say transformer architecture NLP. So this is how a transformer architecture would look like. Okay, it has got lots of components over here, and we have got something called as an inputs, we have something called as an output. So this is the overall architecture that we would say about this transformers. So let's try to understand each of these parts, because it's very important from the examination that you understand the idea behind each and every layer that you see over here in this transformers architecture. So I'll start by getting this file over here. Okay, so this is how our transformer architecture would look like. Okay, we can see this is the transformer architecture. Now let us try to understand what are the key components of this transformer architecture and why this has become so popular. Now let's start by listing down the challenges that we had with LSTM and the RNN, that is the recurrent neural network. See, one of the challenge of this LSTM and recurrent neural network that we had was in the LSTM and RNN. Okay, so the key challenge was we had to pass the data in sequence. That means when we were performing the training, okay, the input data, we have to pass the data in sequence. Like for example, if I have 10 different words, or if I have a sentence which contains 10 words, then I have to pass the words in a sequence. So which means that in the first timestamp, I'll be sending my word one. I'll say this is my word one. Okay, so you can think of it as a word or a token. So first we'll send this word one, followed by word two as an input, and then we'll be sending word three. So this is how the overall connection would look like. Now, the way this was processing is all these individual words were being sent as an input for our sequence model. It can be RNN or LSTM, because that's the model that we have learned that it can process the data in a sequence. So we will be sending it. Now, for the illustration purpose, I'll call this model as an LSTM. Okay, I'll be sending this word to this LSTM. Then the then I'll be sending the word over here, and this it is being sent. It will be sent to the LSTM, and apart from that, we'll also have a connection over here, which says that okay, there is a connection between like one LSTM cell to the another LSTM cell. That means when I'm processing the second word, I'll be getting the hidden representation from the previous LSTM as well as the current word. And this process would repeat for multiple steps. Okay, this is how we will have, and we will have these kind of connection present over here. Now, one of the challenge that we had was using these kind of LSTM structure for a sequence to sequence architecture. Now, I've got a question from you from the last session. So what is the task when we say sequence to sequence architecture? So what kind of task do we use this sequence to sequence architecture, guys? So can you let me know what kind of task that we would have? That's correct. So here it's actually the machine translation. Okay, so during this machine translation, we'll be using the sequence to sequence task. Okay, that is sequence to sequence architecture, because in the case of machine translation, I'll be sending the input, the sequence in one language, and I'm expecting the output in another language. So what it means is, so once I have the output from this LSTM, I'll have another set of layers with me, another set of neurons with me, which would go ahead and generate me the output. Okay, this would help me to generate the output in this manner. Okay, so assuming that this is the translated words that I've got. Okay, this would be the translated words. So the connection over here will be like this. So here, the first set of neurons, which is capturing the input, we will call this architecture as an encoder component. And then the final neuron from this encoder. Okay, this is what will be this output from this final neuron from this encoder will be sent as the input for the decoders. Okay, so this set of neurons that we would have is the decoders. So we have encoders and we'll have the set of decoders. So we have this encoder decoder architecture where using this will perform this sequence to sequence classification. Now, this is the idea behind the usage of LSTM or NNN in RNN in this task of this like sequence to sequence classification, sequence to sequence task, or the sequence to sequence scenario that we have got. Okay, so here in this scenario, okay, so now in this scenario, one of the challenges, okay, we are processing the word by word. So we are processing one word after another in this case. Now, since we are processing one word after another word in this scenario, that's a challenging one. The reason is if I have 500 words in my inputs, then for each sentence, I'll have to pass one word after another. As a result of this, we'll have a slowness in training. So one of the key disadvantages, pass the data in sequence during training, and this results in slowness in training. This is one of the key disadvantage of working with this LSTM. So we need a better way to process the data. And another challenge is when we are working with this sequence to sequence architecture. So one clear challenge is, okay, the final encoder should represent the entire input sequence. So can you see the pressure that this final encoder has? See, like it has got a pressure that it has to remember we have got in the sequence. So that's one of the thing that we would observe right here. So the final encoder should represent the entire input sequence. So as you can clearly see, this is also a challenge. So as you can clearly see, this is a scenario where it's completely dependent on this final neuron. And as a result of this, we'll not be able to learn the overall representation of the data, which will also like affect us in the generation of the output. So these are the key challenges that we had. Now, what they did is like in the year of 2017 or during that time, this research paper was released that is attention is all you need. So using this transformer model architecture from this research paper of attention all you need, we were able to find a way to remember the data over longer sequences. And not just that, we were also able to process that data in a parallel manner. So these are the two main advantages of this transformer model architecture. Now, this has been made possible with the help of important components in this transformer model architecture. They are basically called as multi-head attention, masked multi-head attention, and then feed forward neural network. I'll say feed forward neural network layer. So with the help of these main components, and we'll also have other components as well. If I want to specify the other important components, we'll have something called as positional encoding. So with the help of the positional encoding, the mass multi-head attention, the feed forward neural network layer, and the residual connections, okay, and the residual connection. So we are able to process the data in the sequence. And another best part is we are able to ensure that, okay, we are able to remember over the longer sequences. So that's the main advantage of this transformer model architecture. So all these things that I've just mentioned, these are basically known as components of transformer architecture. Okay, these are called as the components of this transformer architecture. So now that you know the various components of this transformer architecture, so let us try to understand how the data is getting processed inside this transformer architecture. See, in the case of this transformer architecture, the way that we send in the data is we would go ahead and send the data. Like I'll just send the data. Now here the sending the data is nothing but we'll be inputting the tokenized words. Okay, we will have a tokenized words. Now for that tokenized word, we are going to generate the word embedding. So we will generate the word embedding for the given data. So what it would mean is, let's say I've got a sequence. Okay, let's say I've got a sequence. The sequence is, let's consider the task. I have got a source text which says as I love coffee. Okay, now what I want to do is I want to go ahead and generate the translation to German. Okay, I love coffee to German. So it says Ich liebe Cafe. Okay, let's assume this is the target that I want to generate. I'll say my target text is basically this Ich liebe Cafe. So let us consider this very simple example to understand as how this would actually work. Okay, so I have the source text and I have a target text. Now, what is the first step whenever we are sending the data to our input layer? The first step is tokenization. Now, as a result of this tokenization, I'll have three tokens. So I will be one token, love will be another token, then coffee will be another token. So this step is called as tokenization step. So here, as you can see in this tokenization step, I'm going ahead and splitting my sentence sequence into individual tokens. Now, once this tokenization is complete, okay, so what's the next step? See, the next step is generation of input embedding. So the input embedding is nothing but making use of word embeddings. You have already learned about word embeddings. So word embeddings is an efficient way of representing the words in a vector format. Okay, so we would go ahead and generate the word embedding. So here in this case, let us assume that whatever the like box that I'll draw. So let us assume that this orange box over here represents the embedding vectors. Okay, I'll call this as an embedding vector. Assume that this box contains some list of vector values. So this is the output of this embeddings. Now, this word embeddings is what we will be sending in as an input for our which layer will always be sending the input to our encoder. Now, this transformer model has got the architecture which is known as the encoder decoder architecture. Okay, the transformer models has the encoder decoder architecture. So let us try to understand what is this, like how does the data gets processed. See, just like you have observed right here, just like the encoder receives the data, in the same way the encoder component will receive our input and then it would go ahead and send that encoded data to the decoder part. So that's the case of this encoder decoder architecture. So whatever the embeddings that I've got, I'll be sending in for our encoder. Now inside this encoder, we have a positional embedding. We'll come to that very shortly. But the important thing that you need to understand is multi-head attention. So we'll start with something called as self-attention. So what is the idea about this self-attention? So the self-attention, so the self-attention is a layer where this will enable the model to look into the other words in a given sequence while processing. I'll give you a
The
story,
current
okay?
world.
So let's say we
Okay,
have a
so this is the
person.
idea about this
Okay,
self-attention
now we have a
layer.
person called John. John is my best friend.
Okay,
And
so we have
what
this
this John
embeddings
has to
right
do
here.
is,
Now,
he's now
what we'll be
interested in
doing
cooking.
is
In order
Now,
to be
someone
able
told
to
him that
apply this self
there's
attention,
a
I'll
hidden
give
treasure
you a
in the
very simple
library.
example
If
so
you
that you can
look for
relate
a
to it
specific
and get
recipe,
the core
like he's
component
planning
around
to
it.
prepare authentic
Now,
pizza,
let's say, okay,
so
let's
someone told
consider
him
a
that
scenario like if you refer to a authentic recipe which is present in a city's old library, if you follow the recipe which is present in that book, you are going to get an amazing pizza. Someone told him that. Now he believed it. Now what he does is he'll go to that library. So let's say that he'll go to a library now. Now, just for the illustration, let's consider that this is the library. It's a very big library. Now he'll go to this library, and what he does is in this very big library, he'll start searching the book. So, what is the question he has got? His question is, how can I prepare authentic pizza? Now, that's the question that he has got. So what he's going to do with his question is, in this entire library, he would go ahead and search for books. Like he'll search the books which are relevant to his question. Like his question is, how can I prepare an authentic pizza? Because someone has told him, John has believed it, and he's now going around running like a madman to check, okay, where is that book? Where is that book? And his question is, how do I prepare the authentic pizza? Now, with that question, finally, what he did is he finally got some books as well. Okay, so he was finally able to get some books. This is book one, let's say book two and book three. So, and when he's getting the book, okay, so he ensured that he's getting the book only which are related to the pizza. Like he's not interested in any other pasta or any other thing. He's only interested in pizza because his main intention is how can I prepare authentic pizza. So he has shortlisted three books. Now, what he's going to do is he'll refer these three books, and from each book, he's going to get the necessary information. Okay, so maybe he would go ahead and get the necessary information. So let's say this is he'll get this one information and he'll get another information. Let's say this is the another information. So what he has got is he has got the information from three books. Now, once he has got the information from three books, I'll just represent it in a different color, in three different color. So he got the information from three books. Now, once he got the three information, then he has combined all the knowledge. Okay. He has combined all the knowledge and then he came up with his own recipe. So finally, he came up with his own recipe and finally he prepared his authentic pizza. Okay. So he prepared his authentic pizza. So that is what this John has done right now in the story. So someone told him that there's a old library. So you can get a book, recipe book over there that will teach you how to prepare an authentic pizza. Now, with that question in mind, he went to that library. Then he checked out the various books that are available, and then he shortlisted the books which are relevant to him. And from each book, he has extracted some information. And finally, he has combined all the knowledge and he has prepared the pizza. Now, if you have followed me in the story, I'll tell you have understood the self attention. Let me tell you how. So, what this self attention is going to do. Now, the self attention would go ahead and try to learn the relationship between my current word to the other words that I've got in my sequence. So, that's what the self attention is going to do. Okay, that's what the self attention is going to do. Now, when it is processing the current word, so what it has to do, it has to look for the other words for the required information. Just like the John had a question as how can I prepare the authentic pizza? The self-attention layer, I'll mention in a different color. It has got a question as which word should I refer to when I am processing the current word? That's the question that it has got. So what this is going to do, self-attention layer. So just like John referred three books, so obviously this doesn't have the book self-attention layer. What it will do is it will refer to other words in a given sequence. Okay. Now, based on the other words that are, it will look for the other words in a given sequence. And then from each of the words, it will get the importance. from each of the words, it will get the importance which are relevant for my current word. Then finally, just like he has added all the information, so at the end, what we will do is we would go ahead and add everything, add the information. Now, there are some technical terms so that it can be done computationally, because obviously I cannot tell my computer to consider this story and give me. So we'll have to have some technical details, right? So let me add a technical layer on top of this. So here, what I have done right now is the question that John has. Here in my case, the computer which says that which word should I refer when I'm processing the current word. This is called as query. We call this as a query. And just like the John referred to the other words in a given sequence, we call it as key. So query and key. So so what we'll be doing, just like he'll go to the question and search for the relevant books, in the same way, we'll search for this query in our dictionary, like in this keys. Now, at the end, we got the importance. We call it as the values. Now, finally, whatever the total value I'll get, I'll perform the summation. So from this understanding standpoint, we call it as Q component, we call it as K component, and we call it as V component. Okay, the query key values are basically the key components of this self-attention layer of this transformer architecture. Now, let me tell you how it happens mathematically. Okay, you have learned the story, you know, at a very high level. Now, just be with me. I'll just show you in a quick and simple way as how it actually works together. So let me place it on the side. Okay, let's keep our John this side. Okay, now how does it work? So on this word embedding, what we will do is we would generate the three matrices. Okay, one matrix, we'll call it as Q. The other matrix, we'll call it as K, which I'll call it as keys. Okay, and the other matrix, I would call it as value, that is V. So Q, K, and V are the three matrices that I will generate. Now, once I generate it, what I'll do is I'll take a dot product between my word embeddings and with three matrices that I've got, and I would generate the three respective vectors. Okay, so this vector, I'll call it as K1. So Q1, this will be my Q1. This will be my Q2. And this will be my Q3. So how am I getting? By multiplying the X1 with Q, X2, X2 with Q, and so on. So this is, you can think of it as X1, X2, X3. So by multiplying X1 with Q, I'm getting Q1, X2 with Q is Q2, X3 with Q is Q3. So these are my queries. These are my queries. I'll say query. Then what I'll do, in the same way, I'll multiply X1 with K that I've got, and I would go ahead and uh, like multiply it, and I'll call this as K1, K2, K3. Then I will generate the three more values, that is V1, V2, V3. So all of you with me so far? Say if you're yes. So please, if you're with me, please confirm by typing in as yes. Perfect. So we have V1, V2, and V3. Okay. So with this Q1, Q2, Q3, K1, K2, K3, and V1, V2, V3, so we have the respective vectors. Now, here's the important part, and here's a very interesting part that would happen, which will connect us back to the story. So what our John did is, based on his question, he went to the library and searched for the relevant books, and then he found the information by looking into the other books. Now, what we'll be doing in this case? We'll start by focusing one question at a time. Just like he had one question of how can I prepare the authentic pizza, in the same way, the question is nothing but query. So the way this is going to work is, so for this Q1, okay, which I'm having right here, for this Q1, while processing this Q1, I want to know, as for my question, which other words over here can provide me the necessary information, which means I would go ahead and refer to the all the other keys that I have got for the other words. Okay, I would go ahead and refer all the things that I've got in my other words. So this is what I would go ahead and do it. Now, how is it going to happen? Let me show you. It's very simple. So the box that I'm drawing right now is going to just describe, okay, what is it that I'll be focusing on. So I'm focusing on this word Q1 with the other words that I've got with me. Okay, so for this question, that is query, I'll refer to the other keys. Think of it as an individual books in the previous example, the story that I gave you. So what he did is, with this question, he referred to the other books, right? The same thing that we will do right here. Mathematically, what we will do is we'll multiply Q1 into K1. I'll just mention three boxes so that it is easier for you to visualize. First thing that I'll do is I'll multiply 1 and K1. And here my question is same, but I'm referring to the different book. Think of it in that way. Q1, K2. And my question is same, and I'm referring to the different book. So Q1 with K3. Now, when I do this multiplication, just like that, there's a very high chance that I'll be getting a huge value. Now, when we are talking about deep learning, we want to get in a as little value as possible. That's what we'll be most interested, because that will be much easier to process the data. So what I'll be doing right now is, once I have this Q1, K1, we will say that even the research paper talks about the same. We would go ahead and perform the normalization. We will perform the normalize. Now, in this case of normalization, so what I'll be doing is, okay, I'll divide it by the square root of number of dimension. I'll say divide by number of dimension. So whatever the Q1, K1 that I'll got, I'll divide it by square root. I'll just say sqrt of D. Okay, this is what I'll be doing it in each and every value that is Q1 and K1 that I've got. Okay, so this is what I'll be doing. So this is Q1 into K2, and this is Q1 into K3. Okay, now once I've generated this, once I've performed the normalization, the next thing is, obviously this will be in a small scale. Now what I'll do is, we would go ahead and apply something called as softmax. Now, what happens when we apply a softmax? Can anyone tell me what happens when we apply a softmax? So perfect. So it's a probability. We'll be generating the probability score. So what this is going to generate is, this would generate the probability score. So it will generate a probability score between 0 to 1. Now, what I'll do is, I'll just say P1, which is a probability score. I'll say P2, and I'll call this as P3. Okay, so we'll be applying this, we'll be getting this output from this, like P1, P2, and P3. Now, what is the general idea when we talk about probability? The general understanding is P1 plus P2 plus P3 is equal to 1. So this is the general idea of the softmax activation. So does everyone agree with me? So if I add all this probability, I'll be getting the output as 1. Perfect. So now that this softmax is got, now what we will do is, finally, the next step, okay? Like what happens in our story? So here we have 3 values over here. Like he has extracted some values from each of the book. Then he has combined all these values, like combined all the information and prepared his own pizza. That's what John did in his story. So I want to do the same thing. But before I combine all the values, see, this is the value that I got V1, V2, V3. To get the correct value, what I'll do is, I'll multiply P1 with V1, and then I'll multiply P2 with V2, and then similarly, I would go ahead and multiply P3 with V3. So this is what I'll be doing it at this step. So P1 V1, P2 V2, P3 V3. Now once I have it, I would go ahead and perform the summation. Now once I perform the summation, the output that we would get, we'll call it as Z. That's the output of self activation. So self attention. We call this as self attention. So let me highlight in a different color to say that this is actually a different step. Okay, so let's recap. Let's connect to the story so that you'll have a better understanding. Here we've got a question. Question is, think of it as the same original question. How can I prepare authentic pizza? So just like he goes to the library, we already have a library with us. That's the keys. Book 1, book 2, book 3. So from each book, we are going to perform a query. That means just like John will go through each and every book and get the information, mathematically, I'm just multiplying them. That will give me the output. We'll normalize it since we are working with computer to ensure that we do not get a crazy values. So we'll normalize it by multiplying together and dividing by square root of that dimension. Then we'll get the probability scores, P1, P2, P3. So P1, P2, P3 is received after we apply the softmax. Then we'll get the respective values. After we get the respective values, we'll just multiply with our P1 times V1, P2 times V2, P3 times V3, and we add them together. I'll just say summation. That's the final step. We'll perform the summation now. That's the output of self-attention. Okay. This is the overall process that we are going to follow inside the self-attention layer. Now, the key thing that you have to remember is when I'm processing the current word, I'm looking at the other words as well. How am I looking? I'm looking at K2, K3. I'm looking at V2, V3. So as you can clearly see, I'm clearly looking at the other word values. So as a result of this, it's clear to say that whenever a data is getting processed for the current word in my self-attention layer, it would be looking at the other words in my given sequence. So that's the intuition behind the self-attention layer of this transformer model. So folks, is everyone with me so far? Any questions? So if you're clear, please confirm by typing in as clear. Okay, thank you guys, team. So now that this is clear, one thing is pretty clear to you as how exactly is the self-attention is going to work. Okay, this is called as a self-attention. So we have the self-attention, which is part of this multi-head attention. Now the question is, what is multi-head attention? So multi-head attention is nothing but just like you have seen one self-attention layer, I'll have multiple set self-attention layer. Now, why is it? Well, think of an example, like an example that says as dog is crossing the road and it is very tired. Now, if the word it has to learn the relationship between the other words, so it's very difficult to learn everything with a single self-attention. So the idea is we'll make use of multiple self-attention layers so that each and every word can learn its relationship to the other words in my given sequence in a much efficient manner. So that's the idea about this multi-head attention. And then I had initially left something called as a positional encoding. So what is this positional encoding? So to explain you the importance of positional encoding, just observe these two sentences. Okay. Dog is chasing cat. Cat is chasing dog. So if you observe these two sequences, that is these two sentences, you can clearly observe one thing. Okay. Even though the words that are being used is same, the meaning is entirely different. Like in the first one, the dog is chasing cat, and in the second one, cat is chasing dog. Just by shifting the position of cat and dog, the entire meaning of the sentence is getting changed. That means, from the language perspective, the way in which we use the words is going to matter a lot. Now, here in this case, when we talked about one of the best feature of this transformer architecture is it is able to process the data in parallel. Now, when it is processing the data in parallel, how can I differentiate dog is chasing cat and cat is chasing dog? That's a question. Now, how can the system can learn about it? So that's where we require to specify the position whenever we are processing the each word. And that is provided by this positional encoding. So here, if I want to put it simply, so we have a positional encoding. Suppose I'll call it as P1, P2, and P3. So we'll have the positional information for each and every word. Now here for the positional encoding, we make use of sinusoidal function. Okay, we make use of sinusoidal function. We call it as sinusoidal function. Using the sinusoidal function, we will be able to represent the position. Now, what we will be doing is whenever we are sending the data, we are going to add, okay, I'll add the plus symbol over here. We are going to add the positional information to our input data. That is what this plus represents. We will add whatever the output from this positional encoding vector, we'll be adding it to our input data. So that's what happens inside this plus symbol. So you have the input token, generate the word embedding, add it to the positional encoding, and you would send it to the multi-head attention. Now, once you send the data to the multi-head attention, so what would happen? Well, once you send the data to the multi-head attention, you'll get the output from the encoder, you'll have multiple outputs, and then finally you will transform it into a single output. Then over here, you see some kind of a connection that's happening. So there is a connection that you would see at this point. That means whatever my original input data, that original input data is itself being sent at this step. So what is the meaning or what is the reason behind this? This kind of connection is called as the residual connection. Now this residual connection will ensure that we will not, this will minimize the challenge of the vanishing gradient problem. So one of the main problem of working with the sequence-based architectures is the vanishing gradient. Now with this, we'll be able to reduce such vanishing gradient problem. That's one amazing thing over here, guys. So we'll be able to reduce the issues related to the vanishing gradient. That's an amazing thing. So that's a reason that we'll have a that we would have this residual connection. So we will add our original input data to our process data so that we can remember our original image data, original data context over here, and we will normalize it. Then we have a feed forward layer, and which is then sent to add a normalized layer. So we will have multiple such layers. This is what the processing from the encoders would look like. Okay, this is how the processing from the encoders would look like. Then what we have is the decoders. Now what we have is the decoders. Now in the case of this decoders is another set of neural network. It's another set of layers which will take the processed encoded data and then it will try to predict the target. Now whenever we are performing the training, the idea is like this. So if I want to generate my target as Iklebik Cafe, so let's try to mention it. I love coffee. Now, if this is my input, that is, I'll just represent it over here for this LSTM itself. The example, I'll say, I love coffee. Now, I want to generate the output from the decoder as Iklebik Cafe. Okay, this is the expectation that I have from the output. Now, when this is the case, okay, when this is the case of my sequence input and the sequence output, now let's try to understand what would happen. See, whenever I'm generating the output, like especially during the training, for the first neuron of the decoder, what we generally send is we will send a placeholder, which says as start, where by taking this input, this neuron is going to generate the output. See, when you think about any neuron, it will only work when it receives the input, right? Without receiving any input, how can it generate the output? So we have to send in some input. We will be sending something called as a placeholder. I'll say start. which is like an indication that go ahead and start decoding. Then what I'll do is the next input will be basically the first word. For the second sequence, it is ik. And for the next word, it will be libe. So this is how I'll be sending in the data during the training of this sequence model. Now, what am I doing right now? If you look into the target sequence, I've got ik, libe, cafe. What am I doing when I'm sending the data to this decoder component? Can you see? I'm just shifting one step towards right. So do you guys agree with me? I'm just shifting one step towards the light. Like if I've got ik in the first step, I'm just sending the ik in the second step in the decoder. So is everyone with me so far? That is how I'm sending the data. Okay, I'm sending in the data by shifting one position towards the right. So that's how we are going to send in the data. But here's the interesting and the challenging part. Now on top, I have mentioned that this transformer model architecture can process the data in sequence, process the data in parallel. Now, what is the benefit of sending all the words then? See, it's like I'm asking the model to give me the answer and I'm already giving it a solution. So does the model needs to work in that scenario? No, it should not. It will not be able to work because I'm already giving the question and the answer. And what is there to learn for the model? Because I'm just sending in, because from the idea of the self-attention, you have understood that when I'm processing the current word, it will look into the other words of my given sequence. In my case, let's say if I send in the data as it is, it will look at when it is processing the current word, it will look into the next word and it can generate the next word as it is output. So to avoid this situation, we make use of masked multi-head attention. The masked multi-head attention will ensure that whenever I'm processing the data, okay, whenever I'm processing the data for my current input, this masked multi-head attention is to mask the future word. It is going to mask the future words so that it can only look into the current word or the previous words. So that's the role of this masked multi-head attention. Then the output from this masked multi-head attention, along with the the value that I'm getting right here, Q and K components from the encoder, we'll be sending it as an input over here. So QK and value from the masked multi-head attention will be sent as an input. And here at this step, we call it as cross attention. We call this as a cross attention layer. And some cases, we also call it as encoder decoder attention. It's the encoder decoder attention. So here, the reason that we call it as cross attention or multi-head attention, cross attention or encoder decoder attention, because I'm considering the data from my encoder as well as my decoder component. And once it is processed, we'll have a feed forward layer, adder normalized layer, linear, and the softmax. So this is how the overall architecture and the key components of this architecture would work. In each of the masked multi-head attention, it does the same thing. Q, K, and V gets the value, multiply Q into X into Q1. So whatever the X that we have got will get the same. Then we'll multiply Q into K, normalize it by dividing by square root of D. Then apply the softmax, multiply that softmax with P values, then add them together. That would be the output of the self-attention. We'll have multiple such self-attention, so that we'll call it as multi-head attention. That's the core idea about this transformer architecture, which has got both the encoder and the decoder component. Now, using this, we are able to process the data in parallel. And we can also ensure that by making use of the masked multi-head attention, we can ensure that the decoder does not cheat by masking the future words. And the cross attention will ensure that it is considering the decoded input as well as the encoded data. By considering both, it is generating the output. Now, with this architecture, we are able to see some of the tremendous progress and some of the amazing results with this transform architecture. And I can say that's one of the reasons that the people in NLP domain has to know about this transformer model architecture. So I'll take a pause here, guys. So any questions so far? in this transformer model architecture. If you're clear, please confirm by typing in as all good. Or if you've got any question, please let me know. Someone says, can you please explain residual connections again? Definitely. So to understand this, the residual connection, let me just take you through the tensor neural network playground. It is easier for you to, I like for me to draw. Okay, I'll just take you this. So let's assume I've got the neural network architecture like this. Now, what is residual connection? This residual connection simply means that when I'm in this layer, let's say this is my H1, H2, and H3, H4. Okay, I have 4 layers. When I'm pro whatever the when I'm processing the data for this H3, okay, for this H3 layer, the output from H2 layer is being sent as an input for this H3. Now, when I'm getting the data from H2, the information from H1, there is a very high chance that I might lose it, or the information can be reduced from this H1 as well. Now, in such scenario, we will maybe I would go ahead and concatenate, or maybe I will add this to the output of this H2 so that we can ensure that the information from H1 is also carried to the future layers as well. Now, the reason this is important because as the number of layers in my neural network grows, if I do not have this residual connection, then let's say that I have 10 layers in my neural network. Now, from the output layer, if I have to go ahead and update the neurons in my first layer, I'll have to pass in a backward direction. So if the value of gradient is very less, then by the time I reach the first layer, it will be very small and there will be negligible changes in the first layer, which means that the first layer will not be able to train. But if I have the residual connection, at least with this connection, I'll be able to reach that layer faster and ensure that even that layer gets updated. That's the idea and the importance of this residual connection. Is it clear now? Perfect. Okay, so now that this is clear, the overall encoder decoder architecture, now let's look into the types of the model architectures that we have got. See, on the basis of this transformer model architecture, which has got both encoder and decoder, we classify the transformer model architectures as encoder only models, decoder only models, and encoder decoder models. So let's talk about the individual parts. Okay, when you think about the encoder, what is it it's made of? It is specialized in processing my input and sending the data to the decoder. Now, what people at researchers at Google they did is they like since I'm interested, like they said that I'm only interested in understanding how the text would look like so that I can work with it in an efficient manner. So they have used only the encoders of this transformer model architecture, and they have stacked multiple such encoder, and they call the model as a BERT model. And then they started using this BERT model for various tasks, such as the okay. So like in various parts, such as like here in this case, like I want to encoder only model here in this case, like they will get the data, sentiment analysis, that's correct. So we can use it for sentiment analysis, text classification for all those tasks. So they train the model to get the better performance. Okay, then what people at OpenAI did is we are interested in generating the output, a new output. So what they did is they started focusing on constructing the model with the help of decoders only. So the GPT model that we have got, it has been trained with stack of decoder only models. And as a result of this, we call these models as generative models. And they have created this model, trained on a very big, large data set, and then learned the pattern. And using that, we are able to generate the output. And then there's also another architecture, famous architecture in encoder decoders that's called as T5 transformers. This is a combination of both encoders and decoders. So I'll say these are all, I'll say these three are the most common variants of the transformer model architecture. Okay, encoder only models, decoder only models, and encoder decoder models. Okay, so this is the overall idea about the same. And here, so let's go ahead and try to understand about this encoder, decoder, and encoder decoder models that we have got, and let's try to understand as how it is actually trained. Now, let's talk about the BERT model. So they have trained the BERT model. That means this overall large language model that we have got. Okay, this overall large language model has been trained on the two tasks that is called as masked. Let me just tell you team called as BERT. Let me just share you. Okay, I'm unable to recollect it. So it has been trained on, yeah, mask language model and next sentence prediction. So based on these two tasks, the BERT model, that is the encoder only model, has been trained. Okay, it has been trained on the basis of this uh, masked language model. So when I say masked language model, think of it as a fill up the blanks. So in our school, uh, like we had a sentence and we had to fill up the blank, right? What should come in the blank statement in our primary school? Like same way, the BERT model has been trained. And the another thing is next sentence prediction. So it has to get one sentence from us and it has to generate the output in the another sentence. So that's called as a next sentence prediction. So based on these two tasks, the BERT language model has been trained. Then we have a GPT model. So GPT model is called as a generative models here. In this case, this has been trained on a very large data set. We call it as reinforcement learning with human feedback. So you along with some like human supervised learning. So using this technique, the GPT model has been trained. And T5 transformers, it's since it's a transformer model architecture, it is trained and it is having both encoder and decoder. So we use this GPT model for the tasks such as generation, and we use the BERT model when we want to understand the data. It is much suitable for the tasks such as translation. It is much suitable for sentiment classification. The that's where we will be using these models team. Okay, so this is the overall idea of working with this transformer model architecture and the mask language model, transformer model architecture, and the types of this transformer model architecture.